I'm going to talk about what happens to the entropy of a system as that system undergoes a phase change. Here I have drawn a solid, a liquid, and a gas. And I'm going to assume that in each drawing I'm dealing with the same substance, say water. And I'm going to assume that in each case I have the same amount of water, so the same number of molecules. Let's look at what happens at a molecular level. So in case of a gas, the molecules are rather far apart, or they can be rather far apart. And also, they have quite a lot of freedom of movement. As a result of this freedom of movement, there are many states that this particular system, so the gaseous system, can be in. And as a result, the entropy is rather large. In case of liquid water, so in case of a liquid phase, the molecules are a little bit closer together, and they might even interact with each other due to some intermolecular forces. Their freedom of movement, while large, is a little bit less than the freedom of movement available to the molecules of the gaseous phase. As a result, the number of states available to this system are somewhat lower than the number of states available to the gaseous system. So we can say that the entropy of the gaseous phase, the gaseous system, is larger than the entropy of the liquid phase. Finally, if we look at the solid, the molecules there are even closer together. They are packed in some sort of lattice structure. And they can stretch a little bit and they can vibrate, but their freedom of movement is rather limited. As a result, the number of states available to the solid phase is limited as well. So we can say that the entropy of the solid phase is far less than the entropy of the liquid phase. And generally speaking, for any substance, we can say, as long as the substance is pure and we have the same amount of that substance, we can say that the solid phase will have a lower entropy than the liquid phase, which will have a lower entropy than the gaseous phase.